Hi, I'm Dylan Taylor, Chairman and CEO of Voyager Space Holdings.
I'm Ken Eppins, founder and CEO of Orbit Guardians.
Hi, I'm Raphael Rotkin, founder of E2MC Space Ventures.
And I listen to the Cold Star Project.
And I listen to the Cold Star Project.
And I listen to the Cold Star Project.
This show is for entertainment purposes only and is not what is termed professional advice. The Cold Star Project is proudly presented by the Operational Excellence Society. Cold Star Tech is a supporter of the OPEX Society, and Jason Kanigan is a member of its board of advisors. Talk with us at Cold Star Tech to find out what we can achieve together with your Lean Six Sigma or Operational Excellence programs, and check out opexsociety.org to learn more. Today's guest is Dr. Jonathan McDowell. He got his PhD from Cambridge and sort of immediately, it looks like, went to work at Harvard-Smithsonian Center for Astrophysics. As you guessed it, an astrophysicist. He has an asteroid named after him, Planet 4589. Is heavily involved in the Chandra X-ray telescope, which is still, like 20 years later, beaming us back pretty cool images. And he creates this monthly report called Jonathan's Space Report. I think it's a good name for it, you know, it's appropriate. But what I really enjoy is Jonathan's Twitter feed. It's one of the few things that I really look forward to when I go on Twitter, because he is tracking launches and space vehicles, and there's not too many people who are doing that, especially from his perspective. I have really enjoyed watching the altitude charts of Starlink satellites, the small sats, and see how they do. Sometimes they don't do so well, you know. Sometimes they go up, they don't go to their correct altitude, they sit there for a while, and then they come alive months later. At other times they just drop into the sea, so you never really know what you're going to get. Speaking of not knowing what you're going to get exactly, this interview went off in an interesting direction because I asked a question that was not on our notes page, and I was really pleased at where it went. So we're going to talk about black holes, we're going to talk about James Webb Space Telescope, because that's in the news too, a little bit about Starlink, and it's going to be a lot of fun. Jonathan, welcome.
Okay, welcome back, Jonathan. I love having you on. We've had to wait a little bit for this because, you know, everything is good, requires some waiting. So let's talk about space infrastructure. I know Gordon Ressler and I have talked about the space superhighway and all the building blocks and that. From your point of view, what pieces do you believe we should be working on first? Do we need, for example, more crewed flights, more instruments, upgrading the deep space network? Where would you start?
Right. Well, I definitely think upgrading the DSN is critical. I mean, they have been doing some stuff. I know. So the Deep Space Network is something that we on the Chandra mission, which I'm part of, we actually use the DSN to talk to Earth. We're sort of the least deep of the DSN's customers, and so, you know, we're often, okay, we have to reschedule our contact with DSN because this antenna is down for improvements and things like that. So we see them making these improvements all the time. But yeah, we're in a qualitatively new era now in deep space exploration, I think. Mm-hmm. And so it's not just NASA's deep space network. You know, ESA and indeed even, you know, China have their own deep space networks. And I think all of those have got to be upgraded. Although I'm also boggled by the success that hobbyists have had in detecting, you know, radio signals from people like Scott Tilley, right, who regularly pick up telemetry from spacecraft in orbit around the moon. And so, you know, they have a deep space network in their own yard. So, you know, the technology is changing, so maybe we can do a better job of that infrastructure. I also think that we'll need, you know, communications and navigation satellite networks in solar orbit as relays. You know, if you imagine a future in which there's a lot of asteroid surveying and perhaps mining going on down the road, with small spacecraft doing most of it, that small spacecraft may not have the oomph to have a high gain antenna that can talk to DSN easily. They might want to, it may be more effective in the long run to seed relay satellites throughout the inner solar system, and also have those as a framework for navigation as well, help the survey probes figure out where they are. And so I think there's a lot to be done on that sort of infrastructure. The bigger picture of what else do we need in the infrastructure? I mean, there's this question, right? Is the gateway actually useful? Right? As having a space station in lunar orbit to support lunar human surface operations. I mean, it sort of makes sense, but does it really? Is it? Do you actually gain anything versus sending vehicles along each time? I kind of go back and forth on that, and so I think it's really interesting to see how it works out in practice. I mean, naively, yes, it's good. You have something already there that you can stage things on. On the other hand, you have to kind of divert to it rather than going directly to where you want it to go, and you have to keep supplying it.
Yeah.
So whether that balances out in the long run is not super obvious to me.
Okay. Yeah, and I see where you're going with that. I've learned a lot. There's a channel, I think his name is Drakenafel on YouTube and on Twitter, and he's interested in naval history, and he has talked about the logistics of setting up a naval base. And I was fascinated that all these ship people were fascinated with an hour and a half discussion on naval logistics, right? I'm interested, but I didn't think they would be. And I think a lot of the same things that I learned from his lecture would apply over here as well. Like you say, you've got to put stuff there. It becomes a diversion point, and you've got to keep supplying it. And so, yeah, I agree with you. Thought needs to be put on it.
Previously, right, Napoleon taught us that the logistics is key for in the military.
Yeah.
Right. It's also going to be key in exploration and settlement.
Right. Yeah, and the modular replaceable parts that I keep hammering on about are really key here. We need to be able to not just make a thing and put it there, but be able to put that thing there and then pop stuff off of it and replace it with newer things as time goes along.
That's can we get our USB-C standardized for right? But and that was that's one of the problems with the ISS, right? Is that all the modules are just slightly different. And so again, that's an engineering trade, right? Is when you have a generic piece of equipment, it means for the specific thing that you're using it for, it has functions that you don't care about, that you've paid for and you don't use, right? So maybe I get a totally standard laptop and it has Bluetooth, and I never use Bluetooth, or and so in a way it's wasted. But on the other hand, the standardization saving of just having made them all the same, is a win. And so that's an interesting design challenge of what are the things that it makes sense to standardize?
Right.
What are the things that it makes sense to make as optional extras, but still sort of standardized in form? And what are the things that you actually do better just by doing as a one-off? And so it's very easy to take a strong position of everything should be standardized. We should just make 100 of the same thing, and they can do anything. But if it can do anything, then it's super expensive, even mass produced. And so we're I think we're hitting that in the space game, and we've seen it in Earth satellites, right? That you had the sort of semi-standardized buses for communication satellites, where you had the Hughes 601 and so on, that they launched like 50 of, but the communications payloads were super different on each one, and the antenna configurations and so on. Just the sort of other infrastructure was similar. But then you have now, the CubeSats, and the CubeSats are, many of them are they have standard interfaces, and then many of them are just mass produced.
Right.
With the Planet Labs, having very similar, dozens and dozens and dozens of basically the same design. And so I think we're at a point where you can look for that opportunity of oh, we can win by standardization, but you mustn't be too purist
Too
about
rigid. Yeah.
You have to ask yourself, what's the right trade in the situation?
Okay, makes a lot of sense. Yeah. I'm sold. So speaking of infrastructure and satellites and that, let's talk about Starlink for a minute. Anybody who is interested in space should be following you on Twitter. It's a place where you're consistently putting out new information, new data. And what I have found fun over the last couple of years since the last time we did one of these is following your Starlink altitude charts. They're kind of a trend line of altitude, and they'll go up and they'll be at the wrong altitude and dead, and then suddenly some of them will wake up and go right up to the correct altitude and start functioning. Others will work for a while and then drop dead. Right.
Well, I think it's interesting. I mean, what the thing that I learned. So on my webpage, the Star Stats with HTML on my website, I have for each launch, I have a summary chart that I update almost every day on for the 60 satellites from that launch, how did they go up and then down, and so on. And what people, what we found from following that is that for each launch, of order 60 satellites that they launched split into 3 groups of 20. And they go into a drift orbit at 300 kilometers. And then one group almost immediately raises its orbit to the 547 kilometer operational height. But the other 2 kind of stay in this drift orbit for one for 1 month and one for 2 months. And then they orbit raise. And what that does is, because the orbital planes at 350 kilometers process at a different rate around the Earth than the 550 kilometer one, they're essentially changing their orbital planes when they get to their final destination for free. So the differential rate between 350 and 550 gives them that free plane change just by changing the timing of when they raise their orbit. And so, but the consequence is that when you launch in February, March, April, May, June, it's June or July before all of your satellites are in their final orbit. And strangely, when they come down, they also, for different reasons, I think, lower them in stages. And so the fraction of their orbital lifetime in which they're actually in the operational orbit is lower than you might think, because it really takes a significant amount of time on the way up and on the way down. And I think that's something that hadn't been appreciated until a bunch of us started doing these sort of altitude charts, really looking at the data instead of just relying on what the SpaceX press releases were saying. And so I think and seeing a really not most of the satellites, but a really significant number of the satellites being retired after a year in the operational orbit instead of the 5 years that they're designed for. And so, although, to be clear, most of them very few of them are actually fully failing in the sense of just, drifting uncontrolled in orbit and are menace to other things. They're bringing them down actively. But clearly they're finding with a significant fraction of satellites, this communications payload isn't doing what we want. We're going to retire it for safety and replace it or something like that. So there's just enormous amounts of, with almost 3,000 Starlinks up now, there's just an enormous amount of data and insight to be gained by seeing how they operate this complex system.
Yeah, thank you, Dr. McDowell, for some insight there, because you just told me things that I didn't know. And to see the data and watch how the game is being played and inferring some things from that behavior. Very valuable.
Yeah, well, it helps us keep them honest, right?
Well, from what you're saying, they sound like they're trying to be responsible citizens, and not let things run amok.
Right, they're doing pretty well, I think. But from that point of view, whether their system is profitable or not is, of course, a whole other question.
Right.
But in terms of not generating lots of space junk, I think for the most, with some exceptions, they're doing pretty well. But it's important for that data to be public and visible, and people to be able to assess what the impact is of this utterly huge constellation.
Right. And I'm not a launch guy per se. I don't get too excited about it. It's just one part of many, even though that's what the public sees. But from an operational excellence standpoint, which is my vocation, right? I love to see a 25 minute launch and 60 satellites being put up, right? It's a thing to behold when it happens, right? I love it.
It's technically very impressive.
Yeah, yeah. All right, let's talk about black holes for a bit. For those who don't know, Jonathan, that is a major area of study.
My day job.
Yes, through Harvard-Smithsonian. I found a number of news articles about black holes that I'd like to kind of go through and get you to comment on. Back in May, the Harvard-Smithsonian led team imaged SGR-A, a supermassive black hole at the center of the Milky Way, our galaxy. Yes, tell us. Okay.
Yeah.
Okay.
So SGR,
yeah,
right, is the standard abbreviation for the constellation Sagittarius.
Ah, okay.
And we write SGR, but we say Sag just because that tells you you're an insider if you know how to say it.
I am not an astrophysicist.
And in the 1930s, I think Jansky, the first radio astronomer, discovered a whopping big radio source coming from Sagittarius that he called Sagittarius A, Sag-A, which turns out to be a couple of things, including a supernova remnant. He didn't have a very sharp image of it. He was just like, oh, over there somewhere. In the 70s, as we got better radio telescopes, we discovered that some fraction of the radio light from Sag-A was actually coming from a point-like source. And so that was called Sag-A star, asterisk for point-like, I guess. And so the Sag-A, which is a big woofy thing, and then Sag-A star, which is this point-like thing. And it turns out that little point-like thing in the middle is the very center of our galaxy and is the 30 million solar mass black hole monster in the middle that is chowing down on stuff, releasing radio waves as a result.
Okay. Should we be terrified about this? It seems terrifying to me. A supermassive black hole at the center of our galaxy, or even any galaxy. Does it mean that everything's going to get swallowed?
Almost every galaxy has a supermassive black hole in it, we now know. And no, it's been there for 10 billion years or so, right? It's not going anywhere. It's sitting in the middle. And we're not going anywhere. We're orbiting the whole, in the gravitational potential of the whole galaxy. Sag-A star dominates the gravitational field in the central few light years. It doesn't, there's so many stars in the galaxy, right? Well, I guess it's, as soon as you get to the point where there are a few tens of millions of stars within the sphere, and so that's pretty much in the very center of our galaxy. You don't even notice Sag-A star's gravity when you're out here in the boonies of the Orion Arm, where we live. And so from the point of view of its gravity, it's totally not a concern for us. Now, the thing that can go wrong to good galaxies is that if you start dumping large amounts of matter into the center of the galaxy and it dribbles down to the bottom of the gravity well and finds itself swirling around the black hole and going in, as if you feed the black hole too much, it can become what's called a quasar. And so then it starts emitting radiation at the rate of a solar mass turned into energy every year. And it can also, if you feed it just the right amount, not too little but not too much, start squirting out. If the black hole is spinning along its north and south poles, it starts squirting out jets of material at the speed of light, positrons and electrons probably, that kind of destroy a lot of the things in their path. And we do see that a few million years ago, there's these things called the Fermi bubbles that were discovered a few years ago by some of my colleagues at CFA. and they are evidence that there was an explosive release of energy, essentially, a few million years ago, when the black hole chomped down on something big, I guess, and squirted out these jets for a while. And it seems to have quietened down again now. And the really good news is that that didn't come quite in our direction. It seems to be, sort of more 90 degrees to us. And so I wouldn't want to be living in the path of those jets, because if it happens again, you could get fried. But we're not in the path. And so I think that we can, on a, sort of, is it doomed for the Earth kind of viewpoint, we don't have to worry too much about this black hole right now. It's unlikely that in the next couple billion years, say, it's unlikely that it will have another conniption and go quasar. Now, when Andromeda hits us a couple billion years from now, and maybe the two black holes from Andromeda and Argus will merge, and you'll have a quasar for a while, and then gravitational wave burst, all kinds of horrible stuff. That could make it altogether too exciting to live around here. But in the near term, and by the near term I mean the next couple billion years, we should not have to worry about our friendly neighborhood supermassive black hole.
Okay, good, excellent. All right. I saw an article in Forbes back in June about NASA Hubble finding a free-floating black hole. What do you think of this concept? Is it just a theory, or is it real?
No,
Does it have any implications?
Okay. So this, I believe, is work done by my colleague Jessica Liu and her team, and they were looking at and some other folks from Space Telescope were involved, and they're looking at a phenomenon called gravitational lensing. And this is a way to find black holes that you can't find other ways, which is, so what you do is you look at a region of space where there's loads of stars, and you measure the brightnesses of those stars. And sometimes what you see is a particular star that normally doesn't vary on its own suddenly gets brighter for a while and then fainter. And unlike when a star has its own kind of indigestion or something, that brightening and fainting happens in all colors of the spectrum simultaneously. It doesn't happen in the blue but not the red and stuff like that. And what's going on is that a massive object is halfway between you and it, and it's focusing the light from the star like a mirage to get you. So some of the light that ought to be going off to our friends on Krypton or something, instead gets bent around to come to us, as well as the light that would normally come to us. And so you get more light from the star here and less light somewhere else. And so that's called gravitational lensing. And so what you see is a brightening and then a fading as this object passes between us and the star. And so that's one way of saying that there's a mass there, right? Now, sometimes what we do is we see that happen and we see that there is actually, a faint star that's passing along doing the lensing. But in this particular case, there was no star there to do the lensing. There's something invisible bending the light to do the magnification. And so, and the amount of magnification tells you how much mass is doing the lensing. And so if it's, and in this case, it's like 5 or 10 times the mass of the sun. So if that were a star, you'd see it, it'd be really bright. So you have something dark, several solar masses that's got a lot of gravity, what could it be, right? And so it's an isolated black. We're not talking here, by the way, about the sort of supermassive black holes that sit in the centers of galaxies like Sagittarius star. This is much wimpier. This is the dead remnant of a massive star. And so it's a mere 5 to 10 times the mass of our sun. right? Which and so it's a stellar object in some sense, but it's a black hole. And so yeah, this is a great way to find isolated black holes, and it's hard to spot them any other way.
Okay, good. Thank you for the explanation. The warping of light comes into play once again.
Warping of light, you know, if you saw, well, we're going to get onto this in a minute, I guess, but you saw the beautiful picture of the galaxy cluster taken by JWST,
right,
where you see this cluster of galaxies that's a mere 5 billion light years away. And behind it, there's all these other galaxies that are more like 10 billion light years away. And the images are all distorted in these like long sausagey shaped things. And that's because of the gravitational lensing, that the light from them is passing this foreground cluster of galaxies and getting bent. And magnified, but also distorted. And so this phenomenon of gravitational lensing is something that Einstein predicted back in like 1916 or something ridiculous. And it was first seen in 1979 and with the discovery of something called the double quasar. Where you see two images of the same quasar. And one image gets bright and then fades a month later. And then 6 months later, the other image gets bright and then fades. It does exactly what the first one does, but lag, because the path from the quasar to us at the speed of light is longer one route than the other.
Wow.
As the curve is bent, right? And so you can tell how much longer by seeing the lag between what the two images do. I remember as a 18-year-old summer intern at the Royal Greenwich Observatory, the guy who discovered this came and gave a lunch talk and said, I found this really weird thing and I think it might be a gravitational lens. It was such an exciting discovery. And now our telescopes have advanced to the point that we see this phenomenon of lensing happening in all different kinds of situations in the universe. And it's a really powerful tool that we're using all the time.
Yeah, my mind starts to break a little bit when I look out and start to think about the time and looking into the past, looking out there, and like, how do you even operate in that field, right? Because whatever's going on way over there, you're never going to get to it, right? By our conventional means. So let's talk about then the photos. James Webb Space Telescope images were just released in the last couple of days. At the time of this recording, it is, I think, Wednesday, July 13th, when we're doing this. Probably be a month or so later when this comes out. What have those images made possible for you as an astronomer?
Well, I think, and my team are actually just downloading the actual science data as we speak to take a look at it, right? Because it's one thing to see the pretty pictures on the webcast. Right. It's another thing to get the FITS data files and look at the pixels and so on. So where that's my task for the rest of this week. But what I can tell you is this: that the range of data that they showed yesterday really is a taster. It's sort of the appetizer plate, right? Like the house appetizer plate with all the different things to show me what you can do, right? And so we saw this lensing cluster at 10 billions of light years away. We saw the spectrum of an exoplanet only 1,100 light years away. We saw interacting galaxies in kind of the middle universe. We saw beautiful image of the star formation region of the Carina Nebula in our own galaxy, and so they're demonstrating the different kinds of things that JWST can do, and it is I call it a Swiss Army knife telescope. Okay. Right? It's not one of these missions where it's designed to do one specific thing, right? It's a facility where it can attack many different kinds of science questions. And the important thing right now is to get data, usually on things that we've looked at before in a cruddier way with Hubble, right? And then we can compare with this data and go, okay, now I see what JW can do. And that helps me understand what I can ask JW to do. You know, what kinds of things I can and can't do. And for they released this beautiful document called the Commissioning Report, which goes into a lot of detail about how the different modes of the telescope are working. One of the things that I think is going to be challenging is what's called the point spread function, where every picture you have from JW, the bright parts all have these spikes, right? And if you look carefully at those spikes, they're very complex. And so correcting for those, because they're not real, right? They're actually the light bouncing off the different pieces of this mirror support structure, and you know, result of combining the different hexagons and so on in the telescope. And so it's going to be a pain in the rear to remove that signature from the data or account for it. And which is, you know, why they pay us the big bucks. I mean, it's part of the design, and we're, you know, we have to be up for it. But so we're starting to see now, okay, we've known the idealized version of what it's going to do. What will it really do? What are the tricks? What are we going to have to work around? And one of the things you worry about, right, is what's the background? That's to say the noise in the data. And it looks like the noise is pretty low. We can see, we have a lot of dynamic range. We can see a very bright thing next to a very faint thing. And so that's very important. And so we're getting a sense of what the capabilities of the instrument are.
Okay. Yeah. When I first saw the images, I was like, okay, this is cool. This is sharp. But seeing the comparison to similar Hubble exposures, I guess, or what have you, data collection, right, is night and day, right? You could definitely see the advancement.
Yeah.
And
the observing time's a lot shorter.
Right. That too. Right. Yeah. It used to take like a month to do something.
One of the things I know a lot of my colleagues are very excited about is that in the spectra from that cluster image, you can see, you can measure the amount of oxygen in a galaxy that's at a very high redshift. And so you can get enough detail, not just to measure the galaxy, but to see whether it's got more or less chemical elements than you expect. You know, so. And that's one of the key measurements that you want to understand for understanding the evolution of the universe at that phase. And so it seems like, and that's a measurement that people have struggled to make with the Keck telescope and so on from the ground. And JWST goes, oh yeah, you want one of those? Right, fine. You know, 8 hours, got it for you. And so that, I think, you know, so there's several gems in those data sets they released that people are going to be copying on many other objects, and really starting to understand, in particular, that early phase of the universe when the galaxies were just forming.
Okay. Jonathan, this is a question that's never occurred to me before, but you probably know the answer to. Who chooses what JWST does? What it points at, and you know what projects.
The good news is it's the same. The question is the same for all of the space telescopes, and most of the ground-based ones.
Okay.
We're just finishing doing that choice for our Chandra X-ray telescope next year. So what happens is this: once a year, all the astronomers in the world write their little 4 or 5 page essays.
Okay.
I want to look at this galaxy. And this is why it's good. This is why it's important for astronomy to look at this particular galaxy and not some other one. And this is the configuration this is why JWST will be able to distinguish between theory A and theory B, and Hubble won't. And so if we just say, well, don't use data, just use Hubble, right? So show me why it's scientifically important. show me why this is the telescope you should be using and not some other telescope, and show me that the amount of time you're asking for is enough that you're going to be able to actually say something definite, right? You're going to have enough signal to actually distinguish between theory A and theory B. And then those proposals, they're basically grant proposals, but they're for observing time, go into a peer review. And we take, so we maybe get 1,000 of those. And we then get a bunch, we get jury duty for astronomers, right? We get a bunch of astronomers who get asked to come. So not the people on the mission, astronomers selected from the general profession, fly in to some, in the case of JW, probably Baltimore, and we lock them in a hotel for like a week and have them and divide up the proposals into galaxies and stars and exoplanets and so on, and have specialists in each one. And you know, it's sort of like the choosing the new pope. You kind of lock them up until they have an agreement. Then the white smoke comes out. Okay, we have a list of, and say, okay, we're going to do these out of 1,000 proposals we got. We're going to do these 100 projects, and they're selected, you know, on the basis of what's going to give the best science. What's going to give the best science, and so now we have, you know, the menu of the science projects we want to do for the next year. And then it's the mission team's job to go, what order should we do these in? Right? When is JW in the right part of its orbit to look at this? You know, can we do it so that rather than, you know, slewing JW, you know, looking at something over here and then looking at something over there and then looking at something over here again, let's put them in the right order to minimize the amount of screwing around we have to do. And find the right guide stars to help us orient properly. And so there's an enormous amount of work that goes into going from that list to what we call the short-term schedule. Which is, what is JW going to look at in the next couple weeks? And that's now live. I wish I had the URL here. You can actually look up that online right now, see what's JW going to observe today and what's it going to observe tomorrow, and so for the next few weeks, and so that's all public, and so but that's the process, and so it's this annual cycle of you know, putting in your proposal, getting approved, getting the data, and then of course you have the effort of trying to turn the data into science and into a paper and publishing it, and then coming back the next year for a follow-up observation.
Okay, yeah, that was fascinating and far more democratic than I imagined it would be. I felt it would be a little more dictatorial. And
what's nice about it is anyone in the world can apply. You don't have, even for a purely American telescope, and Webb is an international one. Right. I just want to say James Webb is NASA, European Space Agency, and Canada. NASA often forgets to mention that, but it is an international mission. So you know, but if you're from you know, Thailand or something like that, put in your proposal. We won't give you any money along with it. If you're American, you might get money along with the time. If you're not American, you just get the time. But that's enough, and you get the data. The way it works right now, and there's controversy about this, is you have the data for a year. That's it. And after a year, the data becomes public. Right. So that's an incentive for you to publish your paper fast, or you're going to get scooped. Right. And then other people can look at the data, and maybe they're not looking at the thing that you were looking at in the middle of the field. They want to look at something else. And so you get all kinds of serendipitous discoveries. And so the public archive grows and grows, and you can do all kinds of great stuff.
I like that. Smart people have been involved, as you would expect.
It's I think it's a really healthy system. And you know, there are cavils. We've moved recently to a blind reviewing process because there was a feeling that, for example, was a gender bias in who got time and things like that. I think in Chandra we didn't really have so much of a gender bias, but in Hubble there was, and so now you don't know whose proposal it is that you're reviewing. And this is talking about, does that actually matter? Is it in fact relevant that this person has successfully, done similar projects in the past, so they actually know what they're doing, as opposed to someone who's just, never done it before. But the general feeling in the community now seems to be, no, you make it blind. And especially, I'm not convinced it works because the field is so small that it's often easy to guess who it is.
Right. This person's interested in this topic. Yeah.
Right, exactly. And I recognize the style of writing, or I recognize the particular way that they're going about it, and so we're, but we do the best we can. We do the best we can to make it fair for everyone, and to optimize the science, independent of other, considerations, and look at, what's the archive going to be in 10 years time? Is this data we want in the archive, right?
Okay. Yeah, and I'll see if I can find that link and put it in the description. Hopefully I'll remember to that.
I'll send it to you, yeah.
Okay, great. So let's finish up with this then, Jonathan. What are you working on as a scientist and investigator?
Well, I recently finished a paper, published a paper on a distant quasar, my favorite quasar, PG 1407 plus 265. And I discovered that there's a cluster of galaxies that I had thought was going to be sitting around the quasar, but in fact turns out to be halfway between us and it.
Oh.
And so I was trying to figure out whether it was lensing or not, and it's just too offset to be lensing. But it's sort of an interesting new object that we hadn't known was there. And one of the things I'm wondering about is how many. The reason we hadn't seen it before is that this quasar is so bright, particularly the X-ray, that the cluster had been lost in its glare. But with previous telescopes that didn't have as sharp X-ray vision as Chandra does. And so now I'm starting to think about, okay, let's look at other bright quasars and see whether we might have missed clusters associated with that. And so that's one thing I'm thinking about. I'm also spending a lot of my science time on the problem of satellite constellations and how they're going to affect astronomy. So I'm sitting on a lot of committees now that are trying to go, what is the impact really going to be? How can we mitigate it? What is the solution? So, and this is something, it's important. It's like, it's an unfunded mandate for us as astronomers, right? We have to respond to this thing that is affecting us, and we don't have special funding for it. But we've got to look at it because it's going to affect how the profession does its work.
Right. Yeah, and that's been an outcry for a couple of years now, at least, of the streaking across the sky. All right. Well, Jonathan, I appreciate you doing this. If somebody wants to get in touch with you, what's the best way for them to go about doing that?
Where I hang out mostly is on Twitter. And so I'm Planet4589 on Twitter. And if you ping me on there, if you at me in a tweet, I'll usually reply, although today I've got so many responses on the J's website that it's like
32,000 likes on it or something. It was a lot.
And 7,000 retweets. So I was very gratified with that. And also, actually, I'm also still getting, like 2 days ago, I tweeted something at Elon and he responded. And so now whenever you do that, your mentions are, drowning in people talking to Elon for the next week. So hopefully that'll die down soon and I can actually engage again with my followers, which I love doing. Right. Twitter's been a really great place to have, intelligent discussions about space and astronomy.
All right. Well, thank you. Appreciate you doing this.
All right. I hope you enjoyed our talk with Dr. Jonathan McDowell. I had a really fun time with it and learned something. Right? That's what I do this for, is to meet up with these folks, these really smart space defense folks, learn from them and share it with you, okay? So that I'm not just keeping all that precious knowledge to myself. Speaking of special knowledge, precious knowledge, expertise. If you're a defense contractor and you're struggling with bid capture, come talk to us. I will bet you there are whole areas that you have just missed, and it's not because you're stupid, it's just because you're focused on what you're doing and you're in it every day. And to do surgery on this stuff, you got to be outside of it looking in. I've talked to defense contractors who thought that their competitive advantage had something to do with their features. This is not really likely to be true. It's probably something else, and I'd be happy to talk with you and work with you to figure out what that is. So if you want to improve your bid capture rate, have your salespeople feeling successful rather than losing and losing and losing and losing, then come talk to us at Cold Star Tech. Just go to coldstartech.com. You'll see a whole page about bid capture, innovative bid capture, and book a time to talk with us. Thanks for listening.